In this section, we're going to cover some equations that will let us figure out the acceleration if we know other things, or the final velocity if we know some other quantities. So let's just first write them out. Let me write them out as your book writes them, and then maybe give you some other options if you like them better. So our book gives us Vx, but it's the final value, is equal to Vx, but it's the initial value, plus the acceleration value times the change in time, and the change in time is going to be between these values. The other equation the book gives us is xf is equal to xi plus vx, the initial value, delta t plus 1/2 ax delta t squared. And vx final squared is equal to vx, the initial value, squared, plus 2ax times the displacement, delta x. One thing I should note right away is these equations all say in the x direction, kind of implying a left and right motion. But these equations work perfectly fine in the vertical direction as well. So the x is interchangeable with y. But I'd rather give these equations to you in a slightly different way, if you would like to use them that way. Now, this equation looks like a brand new equation to us, I would think, but it's not. It is really just this equation rewritten. So why have this one and this one? So instead of using this first equation, why not use the one we already have? Ax is equal to the change in velocity over the change in time. And we could rewrite this one too, so it's a little bit shorter, so you don't have to write so much all the time. If we take xi and subtract it to the other side, that's the displacement. It is xf minus xi. So we could say the displacement, the change in x, would be equal to the initial x velocity, which I'm just going to write this way, Vxi, I'm going to drop the parentheses, times delta t plus 1/2 ax times delta t squared. I can't really shorten this one up too much except for just dropping the parentheses. Vxf squared is equal to Vxi squared plus 2ax delta x. And don't worry, we'll do some practice with these and actually talk through why each of these are useful. So what I've done is maybe rewritten these in a way that I like a bit better. But our book doesn't give us the last two equations that go with this set. So let me add two more in here. So this next one is going to be the change in the displacement is going to be equal to the final velocity times the time interval minus 1/2 times the acceleration times the time interval squared. And the last one is going to be the displacement is going to be equal to 1/2 times the initial velocity plus the final velocity times the time interval. So I'm going to label these as our kinematic equations. And for any motion that we've described so far, we could pick any of these equations and they would work. They're pretty much redundant. They're just different versions of the same idea. But let's notice what each equation doesn't have. This first equation doesn't reference the displacement at all. So this equation is really handy if we don't know the displacement and we don't want to find it. The second equation doesn't reference the final velocity at all. So it's handy if we don't know the final velocity and we don't need to find it. And this third one doesn't reference a time interval at all. This fourth equation doesn't reference the initial velocity at all. And this last equation doesn't reference the acceleration at all. So if we needed to solve for a quantity, we should pick whichever one of these equations makes that easiest. So let's do this stop to think problem on page 50. A cyclist is at rest at a traffic light. When the light turns green, he begins accelerating at 1.2 meters per second squared. How many seconds after the light turns green does he reach his cruising speed of 6 meters per second? So first thing I'm going to do is make a little sketch of the problem. So I'm going to imagine that this is the starting point, and it's at rest, meaning it's stopped, so Vx would be equal to 0 at that point. And then sometime over here, he's at his cruising speed, his cruising velocity of 6 meters per second. And so I'm going to imagine them going rightwards, and my coordinate system also going positive to the right. I'm going to say that my position here at this time frame is just going to be 0 meters. And the position here, I don't know. So I'm just going to say question mark. The time here at the beginning of the problem, I'm going to start my stopwatch then and just say 0 seconds. And the time here, I don't know. And the acceleration happens during this whole segment, and that had a value of 1.2. And it's going to be positive 1.2 because it's moving to the right with a positive velocity, and it's going to be speeding up. So the signs of these two have to agree. So 1.2 meters per second squared. So there I've kind of organized what I have. The question is how many seconds? So this is my goal here. So let's label these initials, put little i's behind them, and these finals. Now instead of saying an xi and an xf, we could also have said a displacement for the whole time interval, which I don't know. And instead of saying a ti and a tf, we could have also said a delta t, a time interval, which I don't know yet. So depending on how you're imagining it, you can say tf is our goal, or you could say delta t is our goal. Either way. So I want to pick one of these equations with a delta t, because I need to solve for delta t. But I want to make sure that that equation does not reference a delta x, because we don't know the displacement. So which equation doesn't use a delta x? This one. So we should be able to use this equation to solve for delta t. So ax is equal to delta vx over delta t, but I want to solve for delta t, so we have to rearrange the equation. So if I imagine multiplying both sides by delta t, I end up with this. Delta t times ax is equal to the change in velocity. And then to get delta t by itself, I imagine dividing both sides by ax. So we end up with delta t is delta vx over ax. So delta t is the change in my velocity. So that's vxf minus vxi over ax. Vxf was 6 meters per second minus Vxi, 0, divided by the acceleration, and that value was 1.2 meters per second squared. I'm going to rewrite the fraction here, so that way we can see what happens to these units a little bit more clearly. So we're going to have 6 meters per second minus 0 meters per second. And we have this fraction in the denominator, so I'm going to flip it and multiply. So I'll have 1.2 meters in the denominator and seconds squared in the numerator. So then this meter down here can cancel out with a meter in each term of this. So we have a per second and a per second. So then that can cancel out with a second in the numerator. So the second squared will just become a second, canceling those out. So 6 divided by 1.2 is 5, and the units are just seconds. So our time interval is 5 seconds. Now we can use that to find that our answer here is just letter E, but we could also just say, what was TF? What was the final time? Well, delta T is TF minus TI. So we could add TI to both sides. So delta T plus TI is equal to TF. Delta T was 5 seconds, plus TI, T initial, was 0 seconds, and that was equal to TF. For sig figs, I look back at the problem and I see that the 1.2 was considered 2 sig figs. The 6.0 is 2 sig figs. So if I was going to give a numerical answer, I shouldn't just give 5 seconds. I should round it to 2 sig figs, which would actually mean saying 5.0 seconds. For section 6, let's say that it's assigned reading because it's just talks you through the general approach on how to read these problems, how to approach them. I'm reminding you to sketch out a figure. It makes your life easier. And you should also go through all of the blue box example problems and work them out in your own hand. It helps you understand them better. You know, you might not have to solve it exactly like they solve it, but you should get the same answer. And if you don't, you can figure out how your approach didn't agree with their approach. Before I'm done, I should go back and make sure to note one thing. That these kinematic equations only work for time intervals where the acceleration is constant. So if I was going to scroll up here to this graph, during this time frame, the acceleration was constant. The slope here was constant on the velocity graph. So we could use a kinematic equation to calculate stuff from t of 0 to t of 1. But you cannot use one kinematic equation to calculate something in the time interval from 0 to 2. You'd have to break it up into 2 segments. You could use kinematic equations for this time frame, and then separately, kind of as a separate problem, you could use kinematic equations on this time frame because they have different accelerations. One way you can see that in the equations is there's no A initial and A final. There's just A. So for this whole time frame, for that whole displacement, it has to just have one value of A.